means the interacting center attacks.
What happens to the other half of the class?
Locked him in a closet.
Well, if you think this is bad, it's not. When I took assembly language programming myself, I took it from San Francisco State University. But the professor, taught over at UC Davis, UC Berkeley. So he would commute to San Francisco every Monday night to teach that class. It's a Monday night only class. So it's like a 3-hour class with assembly language programming. We take about a 10-minute break in between, but otherwise it's a 3-hour class. The class started off with 60 students in class, and it was in an auditorium. So we have about the same number of students here in this class initially, but in that class, we had an auditorium. Halfway through the semester, which is about this point of the class, we had about 30 students left. At the end of the semester, there were 15 left.
So you're gonna be like that?
No, not yet. No. With this class, I'm not done yet. Not even close.
You don't know.
Yeah.
What was the scary part then? What was the scary part?
The scary part of that class was okay.
Push people.
Well, there were several things. The first thing was that at least with this class, all you need to do your homework assignment is some kind of a Linux box. It can be emulated, it can be a remote box, it can be powered for some of you, right? With that class, we were using the VAX architecture, which is a digital equipment corporation type of architecture. There were 4 hardwired terminals in the lab that we can use to do the homework assignment. Now, remember, initially there were 60 students, 60 students, and there were only 4 terminals to do any type of homework.
That's
How fun.
So I think that really kind of helped trim down the population a little bit. I was able usually to do my homework within 2 days of the assignment, so I don't really get into any problems because no one, when I use those terminals, no one will be using it because they all procrastinate until the last day or the last 2 days. So when I do my homework, there's nobody else in the lab. But when it comes close to the due date, you will actually have a sign-up sheet next to the terminals. So each person can only use the terminal for maybe an hour or so, and then they have to do the round-robin thing. So that would be a prime example of time-sliced, round-robin scheduling. Because you have to time each person 2 hours up. Okay, you have to get back to the end of the line and let somebody else use the terminal. And then the professor was talking about virtual memory also at some point of time. I cannot remember how he got into virtual memory, but he was talking about page faults, operating systems and all kinds of other stuff. So that kind of lost, 1/2 of the class to, well, the 1/2 of the half that is remaining. All right, so the recorder is started already. I'm going to go over the homework assignment because I know that many of you did not do it the way that I thought you guys would be doing it. So you were using your own logic to do it, which is okay. I'm not going to grade it based on how closely your code resembles the way it's supposed to be. So you can do it any way you want, as long as it is still finding the maximum of 3 variables and it passes all the test cases. But I do want to show you mechanically how do we write this program using the method that I was talking about. Mechanically look at one particular pattern, translate it into another pattern, and so on. So I do want to kind of go over that process just so that we know how the process works. Because when we get into some more difficult logic, it might be helpful to have a systematic way of dealing with coding in assembly language instead of intuitively saying, okay, I think I can do it this way, which is not resembling the high-level logic to begin with. Okay, so let's go ahead and get started with this one. All right. So what I'll do is instead of starting with I kind of need to start with this one because I need the C code first. So I will go ahead, take a look at the C code first, which is starting from here. This is line 4, this is line 9. So 4 to 9 yank. And I'm going to write another program, find max3.c. So this one would be a regular C program. And what I'll do is I'm going to translate the C program as far as I can go, and then I'll switch to assembly code as the very last stage of the translation process. All right? Okay. So right now I have a regular C program, so I have to give it all the usual stuff that comes with a regular C program. Okay, are there any questions at this point? Okay. So with a regular C program, I can do quite a few things to test it. If I hard code anything into the program, that makes it kind of hard, makes it kind of difficult to test the program because I have to change the source code, recompile, run it again, and then do all kinds of stuff like that. There are several ways to make it more flexible. You can make it read from standard in. The numbers will be coming from standard in, so you can just give it your test files in that case. So that's probably how I want to do it. Originally, I was trying to use argc and argv so I can pass parameters to the program itself, but I kind of decided against that. So I'm going to use no parameters for main itself. And I would kind of use this logic here. And since I'm using VI, I can set up the tab width to be tab size to be like 2. Then I can do something like, okay, let me, one more time. Come on. There we go. So I can basically insert tab into all of the lines at the same time. I don't have.
How do you do that? How do you do that again? It's really helpful.
Okay, it's greater than on the keyboard, close square bracket, and close curly brace to do it. Okay, I'm gonna write it on the whiteboard. This is the shift operation. This one says, I'm gonna do the shift operation from the current one to the end of something. The end of what? Curly brace. So if you run this in VI, it will basically indent the current block all the way to the next end curly brace. This is why I like VI. Well, one of the reasons why I like VI. Okay, in a regular C program, we do not have access to the registers. So instead of using regular registers, I'm going to use unsigned int for EAX, EBX, and also ECX. All right? And then the next thing I'm going to do is to read those 3 numbers in from standard in. Okay, this is a regular C program. So to read a number in, I need to use fscanf. So fscanf, you give it. Actually, scanf will do because I'm reading standard in. So scanf by default is reading standard in already. So you have to give it a format. What am I reading? In this case, it's a %u for unsigned integer in base 10. And then I give it the address of EAX as a variable in this case. And I will do the same thing to the other 3 variables. So EBX, EBX, and then ECX. So with these 3 lines, I would read the 3 numbers in. And yes, this is absolutely bad programming practice because I'm ignoring the return value of scanf altogether. I'm assuming everything is fine. You guys know that this is not exactly good programming practice, right? Because for any subroutine, any function that returns a value, you really should be using that return value to see something is wrong or not. But since I'm assuming that I'm going to type in the numbers appropriately, so I'm not going to spend any time to do error checking. Okay, because the focus is not that part. The focus is actually how do we translate C code into assembly code. Now this is obviously problematic because I missed all the semicolons. And in C, we also need to have parentheses around the entire condition. So I'm just going to fix the usual syntax stuff related to the language itself, using ampersand, ampersand, and ampersand, ampersand here. And also we need EDX also as an unsigned integer. At the end here, I can do a printf. %u \n for the line feed, and I just want to print the value of EDX without the % because it is just a regular variable in this case, and return 0 at the end of the main function. So I might have left out a few things, and this may not actually compile, but I'll leave it up to the compiler to catch those trivial stuff. Okay. So this is how I would start with a program: is to start with the C code, run it, and make sure the logic is working first. Okay. So let's go ahead and do it. GCC-O find max3. I'm skipping all the linking process because there's only one file. All right, as usual, I have some incompatible implicit declaration of built-in function. Okay, I forgot to do a pound include. That's okay. So we'll go ahead and fix that. stdio.h. All right, so it's it compiles, and now we run the program, and I have to give it 3 numbers to see whether it finds the maximum or not. So let's try 1, 2, and 3. It prints 3 out. Let's try 2, 2, and 1. It prints 2. Let's try 2, 1, and 2. It works okay. 1, 2, and 2. It works okay. So you do have to test it with different cases unless you are really certain that the program works to begin with. Okay. Are there any questions at this point about what I have done so far? I just implemented the program in regular C. Okay. I have to give it something before to read in the numbers to test and then print out the maximum at the end. But at least I now have a way to test whether the logic works or not. So the next thing I'm going to do is to go back into this program and say, can I, change the structure of this program so that it indented a little bit too much because I changed the tab size. Okay. So the next thing I have to do is to say, but in C, we actually do not have the construct of else if. There's only one else for each conditional statement. So the construct of this program is really not like this one. If you look at the actual construct, it is more like this. Oops. In other words, we are dealing with a nested conditional statement construct here. Okay, this is more like what the code really looks like. Okay. The other form is equivalent to this form here. It's just that with the extra open curly brace and the closed curly brace, the structure of the program is more visible. That we have a conditional statement on the outside, but the else has actually its own conditional statement in the inside. Okay. So now we can, if I'm not certain, what I will do is I'll recompile the program just to test it again to make sure that it is still working okay. So 133 has a maximum of 3. 313 has a maximum of 3, and then 331 also has a maximum of 3. If I have a bug, it will show up when I have 2 numbers of exactly the same value and both are maximum. That is actually a more tricky case than the usual 123, 321, 312, and so on. Okay, this is actually more tricky. All right, so this is working, and now I can go back into the source code and start to change the program to a non-structured way of representing the same logic. Okay. To use the non-specific, this would be a good time if you know how to use get or RCS or CVS or one of those revision control programs. This would be a good time to save a particular revision because we know this logic is working fine. Okay, so we want to save this version so that later on, if you think, okay, I might have made a mistake and messed up the program, you can compare that program with an earlier version that works so that you can find out what you have changed, and then hopefully you can find out why the logic is not working anymore. So if I'm not using revision control, I can still do something like this. I can say find max3.c and just copy it to a particular revision. Okay, so I can copy it to find max3_1.c just so that we have one backup of this version that is now working. With that backup, I can go back in, and now we can make some changes. The first change I'm going to do is only apply to one of the 2 conditional statements. I will not deal with both at the same time. I will only pick one to deal with. Whether you pick the inner conditional statement first or the outer conditional statement first doesn't really matter. Okay, you can use pick one or the other, doesn't matter. So I'm going to pick the outer one first. If I pick the outer one, I will change the structure of the program so that I will look for the negation of the original condition, and say that if the negated version of the original condition is true, go to the else label of the first conditional statement. And instead of having the else here to correspond to the if, I'm going to change this to a label definition of else if 1 colon. And then on top of this, I also need an unconditional go to here to go to the end of the first conditional statement. And the end of the first conditional statement is all the way down here. Are there any questions about this particular modification of the original program? In other words, I'm just following my own procedure that we talked about on Tuesday to convert a structured conditional statement into something that is flat, that is not structured. Are we still doing okay so far? But everything is still in C. Okay, it is still, everything is still in C. It should still compile, except for the missing semicolon on certain lines. I can spot a few. Well, one right here. All right. So let's go ahead and test whether this program works or not. Okay, because it is supposed to be functionally the same as the previous one. So I'm going to recompile the program, run it again, give it the test case 133 works, 313 works, 331 also works. So I'm fairly convinced that I did not mess up the program or the logic of the program. Now I look at this program and go like, we have a negation on the outside and a conjunction on the inside. So if I use the mechanical process to do this, it's going to make the program really, really long. So instead of doing that, I'm going to use De Morgan's law. De Morgan's law says something like this. If we have a negation on the outside of A and B in the inside, this is equivalent to not A or not B, and not A, not B being, their own things. Are we still doing okay so far with De Morgan's law? We kind of mentioned that last time. So we'll go ahead and apply this transformation first. So that means, now if I do something like this, what I would do is to do something like this, okay? I will make a copy of the line that I'm translating, and then clone it, and then change the clone. So this way I can refer to what it used to be, and also what is the current new form. In case I made a mistake, I can go back and say, okay, what was it like before? It was like that. Did I make a mistake somewhere that messed up the logic? I can at least make that comparison relatively easily. So I'm going to do this part here. Okay, the negation goes into the inside, and then the conjunction becomes a disjunction, and I have to redistribute the negation also to the other side, like so. Okay. Are there any questions about the application of De Morgan's law? The negation of A and B as a whole is the same thing as not A as a whole or not B as a whole. And that's all I'm doing here, is that one little transformation. Is that okay? All right. Now, even though I am almost 99% sure that I did it right, I'm not going to take that chance. Okay? In other words, I'm going to waste 30 seconds to test this before I move on. Why would I waste 30 seconds on something that I'm 99% sure?
Because there's a 1% chance you're wrong.
If that 1% chance happens and I did not test it, it's going to cost me a lot of time down the line, because I would have made a lot more changes and then the program doesn't work, and I would have no idea which modification made it not work. So I would much rather spend that extra 30 seconds here just to double check, make sure that it is still working before I move on. Now, at this point, you will probably see that, this is kind of boring. I'm feeding it the same 3 test cases every single time. So is there a better way to do it? Well, I can create, sample input files and, just kind of use redirect to redirect into it. I can even write a script to compare the output of the program with the expected output also. So that way I don't have to, do it by hand. But, it's not too bad in this case to do it by hand. So I'm just going to do it by hand, just because I'm too lazy to set up the infrastructure to do it. All right,
Well,
but
show us.
it's still working. Okay.
Didn't know that.
All right. Well, in the best case, you can also set up a make file so that the make file also includes the verification part. So you can say make verify, and it will trigger the logic to double check that your program is still working fine. All right. So that part is working. So now I can go in and make some modifications. So once again, I comment out the code that I'm supposed to change, and then I say, well, this looks kind of cumbersome because I'm saying the negation of greater than or equal to. Might as well just say less than. Is that making any sense? Because not greater than or equal to is less than. Yep. Yeah. 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 You can always do it frame by frame afterwards. Because it's all getting recorded. And I'm pretty sure I cannot do it faster than 15 frames per second. So I'm changing the program by simplifying the logic here. But once again, even though I'm 99.9% sure that this is not changing the meaning of the logic, guess what? I'm going to test it. I'll double check. Okay? All right. I'm going to check the program. 331. Okay, 133. And the third one is 313. All right. So it's still working okay. No problem. Go back to the program. And this time I'm going to apply something, a little bit more change, because at this point there's nothing I can do, to make this any more simplified. So it is time to get rid of the disjunction this time. How do I get rid of the disjunction? Using additional if and go tos. Well, in this case, I have two ways to go to else if one. The first one is just when EAX is less than EBX, because it's a disjunction. If one of the conditions is true, I'm going to do the branch. So that's why I can separate it into two parallel branches. So once again, before I make changes to this one, I comment it out, and then I copy and paste it. So this way, I will separate it into two lines. The two lines are about the same. Each one will go to else if one. And then the second line, just to make it look right, this is how I do it. Okay. So once again, I'm not losing track of the earlier revisions of this line, because those are all commented out at this point. But they're still there. Okay, it is still represented in the comments of this particular program. This is a relatively big change, so I'm going to test it. Okay, I'm going to compile the program, test it first to make sure that this is working. So GCC, and then we basically run the program with exactly the same test cases. And it's still working okay, as far as I can tell. All right, so this part is all done. It's time to move on to the inner conditional statement. The inner conditional statement has pretty much the same stuff. So if I look at the outer conditional statement and say, if we can do that conversion with the outer conditional statement, we can probably do something about the same with the inner conditional statement. So instead of going through the entire process all over again, I'm just going to say, hey, we can probably just do something a little bit more simplified and convert this to two conditional statements. Each one is only looking for the less than, and then go to else if two. And then we have else if two defined here. And then after the then branch, we have to have an unconditional branch to the end of the second or the inner conditional statement. And the end of the second conditional statement is all the way over here. In other words, I'm just borrowing all the stuff that I learned from the transformation of the outer conditional statement and just mirror everything to apply to the inner conditional statement. Are we doing okay so far with the approach of doing the homework assignment. Now, if you're not comfortable making that jump, you can apply those steps one by one also. I mean, nothing says that you cannot apply those steps one by one. Okay, but I'm fairly sure that this is working, so I'm going to test the program. Oh, okay, syntax error on line 23. So I go to line 23, and it's because okay, I did not even bother to read the message itself, so I better read it first. Okay, label at end of compound statement, and if to label at end of compound statement. Oh, I think I know what it is. Okay, the compound statement is referring to the open curly brace and the end curly brace. I really don't need the curly braces anymore, because remember, this program is now unstructured, so I can get rid of the open curly brace and the closed curly brace, and I think that should get rid of that particular problem. And run the program again. Okay, seems to run. All right, so the program is still working, which gives me, enough confidence to basically say, okay, at this point, there's nothing that I should do anymore in C, because there's nothing more to reduce. Because everything is now reduced to something that I can implement in assembly language. Now, before I go to the assembly part of this code, well, I'm thinking about whether I should do it or not. Okay, let's just take a look at every single thing that I'm supposed to convert. Scan, I don't have to convert because the GDB will basically be used to inject values into the registers, so I don't have to deal with these 3 lines in assembly. This line, how do I do it in assembly? It is a comparison followed by a goto, which means it is a conditional branch after a compare. Okay, and do you guys still remember the square and the triangle? A conditional branch, following a compare, a conditional branch following a compare instruction. There's a specific way to read it, so I think I can translate that into assembly code into 2 instructions. The line right next to it, same thing. What about this line over here? Can I do it in assembly?
Yes.
I want to copy the content of EAX into EDX.
Move.
The move command, okay, the move instruction. How about this one? It's an unconditional jump to end if 1. JMP, okay, and then the rest are pretty much the same stuff, all over again. So I'm fairly sure that we can do this conversion now into assembly code. So what I'll do is I'm going to take a look at this portion, only the portion that is relevant to me, starting on line 9 and ending up on line 25. So 9 to 25 yank, which is the same thing as copy, Control C, and then I go to the assembly version of this program and do a paste. Okay, so I'll do a paste over here between L1 and L2. And of course, because this is in C code, it's not going to assemble using the assembler. So what I need to do is to go from 19 to here. So 19 to this point, replace the beginning of each line with a pound sign followed by another pound sign. The double pound sign is not exactly needed in this case, but when we have to feed everything through the C preprocessor, the double pound sign will be needed. Okay. So now I have just created basically a large chunk of comment for my assembly language program, because I want to interleave my assembly code with my C code. So this way I can look at one line of comment and look at the implementation of that C logic. So this way it's easier for me to see, okay, what exactly, how am I translating this line here? So here we will do the actual translation. The translation goes like this. Okay, for those of you who may not remember this part, is if I have a conditional branch in C that looks like this, if A some kind of operation B as a relational operation, and then we go to label L, this translates to assembly code that looks like this, with a compare instruction and a conditional branch instruction. The conditional branch instruction will branch to the same label. The compare has to flip the order of the comparison, So B would be the first operand, and A would be the second operand. And this part here is the same thing as the OP. If this is less than, this is L or B, and so on. Okay? So I'm going to look at this template here, and then look at the code that I'm supposed to translate, and just mechanically perform the translation from C into assembly. Okay, so we have a compare instruction followed by a branch instruction. The label that I'm branching to is else if one. Okay. All right. So the compare is going to be a compare long because we are dealing with 32-bit registers. So we have to list EDX first because it's on the right-hand side. The right-hand side thing has to be the first operand, and then the left-hand side would be the second operand, which is EAX in this case. And then this conditional branch instruction is going to represent less than, because that's what the C code is specifying. Now with less than, we have to choose between two alternatives. One is JL and the other one is JB. Which one should I use in this case?
JL.
JB. Because it is unsigned. Okay? Unsigned is easy as ABC, so that's why we have to use the AB and the C for unsigned comparison. Okay? So this is JB for below in unsigned. Okay? And now the unfortunate part about this translation process is I can no longer do it, step by step. Okay? I have to translate the entire thing, in one shot and then test it, after that. All right, so this is the first one that I translate. Here's the second one that I'm going to translate. So we have another compare long instruction. Reverse the order of the operand. So ECX has to be the first one, and then EAX is the second one. And then once again, we have a JB instruction here because it is less than or below, but it is for unsigned. And we are also branching to else if one. This one is relatively easy because we have a move instruction so that we can copy the content of EAX to the content of EDX. This one is also kind of easy. An unconditional branch to end if one is just jump to end if one. Are we doing okay so far with the translation process?
JB is equivalent to J and A.
No, it is not. Because not about also includes the case of equal, of the case of equal to. So technically it is not the same, but with this program you may not see any difference. Okay? But technically speaking, J and A is not the same thing as J. JL? It will work for half the cases.
Oh. I think we're supposed to be on is signed, yeah, signed.
I don't know. I use
JB and JC
JL.
are exactly the same thing because the carry flag is also the forward flag.
From what we were given, the very first condition, it was EDX equals EDX, but out there that EDX equals EDX. Did I copy that wrong?
I copied everything from the original C code.
I mean, from the original C code, I had EDX equals EDX. I copied it wrong then.
The instruction itself is
Just
up
have
here.
EDX.
That's copying EAX to EDX.
I must have copied it wrong.
It says that it's supposed to be signed.
It's supposed to be signed.
Yeah.
Doesn't.
Did it say signed?
Hopefully.
They're not. I changed it from Find Max to Wicked. Not cool. All right, so I'm still getting through the whole translation process. Else if one as a label is else if one as a label. That part, that's the only thing I can preserve between the C program and the assembly version of the same code. All right, same thing here. Okay, so I have to translate this one, which starts with a compare long instruction. And remember to flip the order of the operands. So it's EAX versus EBX. And then it's a JB because the original relationship here is less than, so it's a JB for below to else if two. And then same thing over here, compare long ECX this time as the first operand, and then EBX as the second operand. And then the JB, a conditional branch to else if to again. This one is copying EBX to EDX, move long EBX to EDX. This one is a unconditional branch to else if to, so it's a JMP jump to end if to. And then we have else if to as a label definition. It is the same as in the C code. This one is copying ECX to EDX. You know what? At this point, I'm completely lost as far as the original logic is concerned, but I don't care. That's the whole point of the translation process. If the C code is working just fine, that means all of those statements are working just fine. So right now, I'm just mechanically translating the instructions, basically one to one. Okay, I'm completely lost in the original algorithm. I have no idea where I am currently in the original algorithm, but I don't need to know that part. So move long ECX to EDX, and then define the label end if to over here. Define the label end if one over here, and I should be done by now. Okay, barring any type of syntax error and some stupid mistakes, I should be done. Any questions about this process, the translation process? Did you guys see that I have distinctly two stages to the entire thing. The first stage is completely in C and not in assembly at all. I only switch to assembly once I have simple constructs that I know there's a one-to-one correspondence to assembly instructions. Is that okay so far? Now, I know this logic may not be the simplest. I know some of you turn in homework assignments with far fewer instructions and lines, but this is the mechanical process to do it. Okay, so we'll give it a try. G steps -o find max 3.0 find max 3.s. Wow, I'm impressed. I usually put in something that's wrong and it's gonna, bark at me. Okay, maybe I'm not out of the woods yet, because if I forget to put a % symbol before one of the registers, it would not come up by the time I assemble. The linker would be the one that complains about it. Does that make sense to you? No? Okay, let's go back and take a look. Okay, let's take a look. Oops, not the C code. I want to look at the assembly code. Okay, so if I pick one of the registers here and say, so let's say I forget about this % symbol. Okay, so it's EBX instead of %EBX. The assembler would not complain. This is perfectly okay as far as the assembler is concerned, because without a % symbol, without a dollar symbol, and just a name, this is the direct this is a direct operand. Which means, as far as the assembler is concerned, the assembler is saying, oh, I can see that you're using EBX as a label. But the label is not defined anywhere in this file. The assembler is going to say, oh, that's okay, because I think somebody else might define that label. It's okay, not a problem. The linker is going to bark, because the linker will say, hey, who's defining the label EBX? Nobody? Okay, now we have a problem. Okay, so that's why sometimes when you miss something, the assembler will not catch it. It's the linker that's going to catch it. Okay, so let's go ahead and just keep it the way it is and see what the assembler is going to say and what the linker is going to say. Because I think if you get exposure to the kind of error messages that you can get by actually introducing mistakes into your program, by the time you see those messages without the original intent of testing it, then you know what can cause it to happen. So let's go ahead and do it. Okay. Oh. I did not intend to encrypt it. Assemble again. See, the assembler did not complain at all. So let's see what the linker is going to say. LD-O find max 3 as the executable, not -O, find max3.0 as the input file, and it complains about undefined reference to EBX. That is exactly what's going to happen. Okay, so this is useful to you because someone in this class at some point is going to forget a percent somewhere. Okay, and this is what's going to happen. Is that okay? I think most people will forget completely what I just said in 15 minutes. It's like, what? What did you say? All right, so we'll go fix it, and it will even tell you which line to. It will tell you that it's actually on line 23 of the source file, which is really, really helpful. So on line 23, we forgot this percent symbol. Okay, fine, we're gonna fix it. So we'll reassemble, relink, everything is okay now. So now we have to use GDB to test the program. GDB find max3, put a breakpoint at label L1, run the program up to label L1, and now we're going to inject some values into EAX, EBX, and EDX, EAX, EBX, and ECX, continue the program up to L2, and then we'll take a look at EDX and see if EDX has the correct value. So we'll do a set EAX to 3, set EBX to 1, set ECX to 3, and then we have the, sorry?
Do the ATX to 4 or something? Have 3 different values?
Say again?
Have 3 different values? 314 or something?
You can do 314 if you want to, but I'm going to use 313 because that's the test case that I have been using, the whole time. When you test your program, you can change it to 314, but I'm using 313 here.
Well, what if it's not like having the values for using 2 of them? Like, that's one thing I was having when I used 2 of them, the same ones, I wasn't getting the error. But as soon as I change my value, it's having an error because
it depends on the logic. Some logic well, you have to kind of test it with all the different types of combinations, right? Okay, set a breakpoint at label 2, continue execution. Now I'm at label L2. Take a look at IREDX, has a value of 3. So as far as this test case is concerned, it's working okay. Okay. So when you are really testing it, doing this way is very, very time consuming, and then you have to go through a lot of typing. So if you're lazy like I am, then you're gonna do it like this. So you have all the test cases encoded in here. Just do whatever you think is the best test case, and then just make copies of this, or you can make you can also run multiple commands in here too. So it's up to you to decide how you want to create additional test cases. But I'm just going to create additional test cases like this. So simple test case 2 is going to have the other test case of 133, and then simple test case 3 is going to have 331 as my test case. All right. So now I can run GDB. GDB find max3 as the executable, and then redirect the input from simple test case.gdb, and it will run it, and you can kind of see the output, which is $1 equals to 3. That's the output of the program, okay? And I'm just running it using a script. And to test the other 2 test cases, just change simple test case to simple case to simple case 2, and then to simple case 3. So this way it's a little bit faster to test your program because you don't have to type in all the commands by hand anymore. Yep. Because I did not actually run the entire program through. I stopped at label L2, and then I say quit from the debugger. So the debugger is forced to kill the child process of 5345, which is started by the debugger. So are there any questions about the process of working on this particular homework assignment? How many people did something like this to get the homework assignment done? Okay. And I know some of you actually work out the different logic completely intuitively and just coding in assembly. That's okay too. Except that approach may be you may get into difficulty later on when the program gets more and more complicated. All right. So that's the homework assignment. Are there any other questions related to this homework assignment? Yep.
I was curious, what kind of penalty is there if I didn't see that now it's unsigned instead of signed?
Not a whole lot. Not a whole lot. Because that's really just a JL versus a JB.
What is the whole lot? How many points?
I have not decided yet. Depends on my mood when I'm bringing it. I just need to get a lot of chocolate first, and then it will. Okay, question.
What about rather than compare along with
Okay, the question is, what if instead of CMPL, you specify CMP? Well, technically speaking, for this program, CMPL and CMP are exactly the same because when you specify the registers as EAX, EBX, ECX, and EDX, the implied width is 32-bit already. Okay? So as far as functionally speaking, the program is doing okay. However, it is not a good habit not to specify the width. It's not going to bite you this time, but I can promise you that one of the homework assignments that we'll be doing soon will be very sensitive to the width of operation. So if you have a habit of leaving out the width of the operation, that's going to bite big time later on. Okay? Guaranteed, promise. It has to do with string and character, processing, which we'll do later, because we first have to know how to read something in and print something out, and then we can start with those algorithms that can process, string character by character. Yep.
Are we going to use other negation laws other than De Morgan's?
Other than De Morgan's law? You can use some other ways to do it.
Negation laws. Okay.
Yep. All right. So now that we have this one out of the way, we can go back to the topic that we were talking about before. How do we request the operating system to do something? Okay, so we are now in topic 6. We are basically in this topic here, interrupts and system services. And those two concepts may not look like they're related at all, but they are. All right. So what we did last time on Tuesday was we talked about how you do not want to just make a call to request the operating system to do something for you. In other words, the user process or the user program should be running at a lower privilege. You can ask for the world, but the operating system should have a way to say, not going to do it. Okay? That was the conclusion on Tuesday. You guys do remember that? Okay. So we want to have a mechanism that can do that. In other words, you can invoke the operating system. You can say, hey, operating system, I need you to do something for me. Okay, and you can send your request. But the operating system should have a way to say that not going to do it. Okay, and come back to you with a status and say that nope, cannot do this. Okay. So now the question is, what kind of mechanism would be suitable to do something like this? You are running, your user process is running at a low privilege level because 1, you don't want to mess up the operating system. 2, you don't want to mess up other programs running in the system at the same time. So that's why your own process is running at a low privilege level, which means it only has access to certain parts of the memory space. It can only do certain types of file operation as far as the operating system is allowing. On the other hand, the operating system itself must have a much higher privilege level, right? Because ultimately, the operating system or the kernel, the Linux kernel in this case, is the one that has to tell the IDE controller or the SATA controller what to do, what to write onto the hard drive, how to allocate memory from your actual physical RAM, and so on and so forth. So the operating system, the kernel, actually need to have full access to your entire hardware platform. So the question now is, how can your program start with a low privilege level and somehow trigger an operation that requires a high level privilege level? And when it's done, it will drop back onto your lower privilege level so that you do not accidentally inherit the high privilege level of operations. That is the question. What kind of mechanism is suitable for that type of thing? So in order to understand that, we'll start with interrupts. Okay? And interrupts, seems like a concept that has absolutely nothing to do with what we are trying to do here. What exactly is an interrupt in the context of operating systems and low-level type of programming? Well, let's think about the DOS prompt. Okay, I did not misspell it. I did say DOS prompt. Okay, not command line interface. So we are going back in time to the DOS days. Okay, early 1980s. Okay. Okay, with a DOS machine, IBM PC running DOS, the original DOS, it gives you, what is the user interface of the original IBM PC? Does it give you somewhere to click? No.
It's a blinking little cursor thing.
It's a blinking cursor on the screen. Okay, it's waiting for you to type something on the keyboard, right?
It's green.
Okay. Can you have multiple terminals at the same time? No, you have only one terminal. Okay, that's hardwired to the entire thing. Okay, can you have multiple processes running at the same time with the original DOS? No. Okay, so all of the nice things that we can do now, they're all missing in those days. Okay, fine. So if you are the person who is writing DOS, okay, you're actually the person who is writing or developing DOS, how would you do this? Okay, you're writing the program that is waiting for someone to type something on the keyboard, waiting for the enter key to be pressed so that you can process what has been typed on the keyboard earlier. So what are you going to do to wait for that input? How do you process the user input with the keyboard?
Just wait.
Sorry?
Wait for input.
Wait for input. Very good. You're going to do the polling. Okay, it's called polling. P-O-L-L-I-N-G. It's called polling. In other words, let's say I'm the operating system, okay, and I'm trying to pick on Chris today. So Chris is my keyboard controller, which is a hardware device that the processor can require. Okay, so I'm going to say, keyboard controller, do you have a key for me? No. Keyboard controller, do you have a key for me? Yes. Okay, grab it. Okay, keyboard controller, do you have a key for me? Yes. Grab it, process it, store it into a buffer. So I'm going to keep processing that. So let's say the end user just walked away and there's no cat sitting on the keyboard. Okay? So I'm going to ask you the question again. Is there any key event? No. Is there any key event? No. Is there any key event? No. And I'll keep doing this. Okay? Because it's called polling, which means I'm in a tight loop. It's basically a loop that looks like this in C and C++. While no key event, semicolon. Okay? So that loop is really tight, and it's just going like this. Whenever there's a key event, it gets out of the loop. I do one processing. I'll stash that key into a buffer, and then I'll go back into that tight loop again. Would that be a problem in the DOS days?
No.
No. Why would it not be a problem in the DOS days?
One DOS.
There's only one command prompt. There's no multi-processing.
There's only one process running, and it's that.
Exactly. What about power consumption? Surely that has to be a problem.
Well, it's a desktop computer. You don't have a battery you have to rely on or anything.
Well, exactly. They did have luggables back then, but those were not battery powered either.
Well, the other thing is that the standards that they use today didn't exist for power consumption and stuff like that for computers.
That is correct. Yeah, they did not. People were not power conscious, when it comes to personal computers. Yep.
I was just thinking, switch to GTY1 to see if people have an idea what you're talking about. Control F1.
Control F1.
Control F1.
Oh, Control Alt F1. Like this.
Yeah, you should have switched to GTY. Yeah.
Yep. Well, it's kind of tiny. You cannot see it, but that's basically what the DOS prompt looks like.
Exactly.
But even this is not a good parallel because I have actually several of these virtual terminals. But in DOS, there's only one, right? There's only one.
You should take them into Grub Rescue Mode.
Grub Rescue Mode would be close, but I have a suspicion that Grub is actually interrupt driven as well. Probably. Yeah. Okay, so when do you think this approach of doing things first run into problems?
As soon as there was
DOS 2.0, not a problem. DOS 3.0, not a problem. So we keep using DOS, and eventually what happened?
Windows comes out.
Windows came out. Okay.
But
So
it's
when
still
Windows,
DOS.
yep, go ahead.
But interruption was present in DOS because it has multiple
absolutely.
input devices.
Absolutely. You know, the whole concept of hardware interrupt existed. The concept of hardware interrupts predate DOS completely. It's just that software people were lazy and not use it.
Steve Jobs.
Okay. Software people, yes, developers like us. All right. So it was never a problem until we got into Windows. Okay. So what is Windows 3.1? What does it do? What is the biggest feature of Windows 3.1? You can run multiple things at once, right? You can run multiple applications, all at once, and they all seem to be working all at the same time. Remember last time I explained how that works? It's called cooperative multitasking, which means each process, each application has to do like, okay, I'm gonna do something. You know what? I think I just used up a lot of processing time. Okay, please, it is your turn to do it now. Okay, and in return, you are going to do the same thing, and then the third process will do the same thing, and it will go back to be, it's going to be going around in a round
Kind of like the
robin way.
4 terminals at your college.
Sorry?
Kind of like the 4 terminals at your college.
Kind of like,
When you were doing the assembly class.
1 hour and next.
oh, okay.
Yeah, that's what I mean.
It's cooperative. And here comes, somebody clicking that DOS box, icon and say, I want to do something in a command line interface. Now we have problems. Because, all the Windows applications are cooperative. They all know, okay, I'm going to do a little bit of processing, I'll pass control to the next one. And here comes the DOS prompt thing. Once the DOS prompt gets control, what does it do? Keyboard controller, do you have a key for me? Keyboard controller, do you have a key for me? Keyboard controller, do you have a key for me? And it's not going to stop. And then all the other processes cannot get any processing time anymore. So there goes the pretense of multiprocessing in the early versions of Windows. Okay? So what is the culprit? Why is it working like this? Why is it not working? Because of polling. Okay? It's all because I'm polling the keyboard controller all the time. So what is the alternative? What is the alternative of keep asking the keyboard controller, is there a keystroke event?
Wait for the keyboard to tell you.
Exactly, waiting for the keyboard to tell me, which is what a lazy person should do, right? So has anyone come visit me in my office? Okay, a few people. So what do I usually do in my office? Trip. Definitely not grading your exam. Recharge. Recharge. Okay, that's a good word to describe it. I usually get into low power mode, let's just say. Okay, conserve power. So, okay, so in other words, I'm not polling. Okay, I'm not constantly calling out and saying, is there someone standing outside my office? No response. Is there someone standing outside my office? No response. Is there someone standing outside my office? I do not do polling. Okay, what I do is interrupt driven. Okay, I fall asleep in my office. So here comes Chris with a question. So how does he get my attention?
I stand there and watch for 5 minutes.
And then he knocks on the door, right? He knocks on the door to get the attention of the processor. Okay, so I will wake up and then I'll do something. I'll respond to whatever his question was, and then when it's all done, Chris would leave my office, and then what do?
Go back to sleep.
I go back to sleep. Okay, all right. That's interrupt driven. Okay, that is the whole concept of interrupt driven, which is we don't do anything about polling. Okay, you wait for the device to tell you, hey, I need you to do something. Okay, you do not ask the device repetitively and say, do you have something for me to process? Do you have something for me to process? Do you have something for me to process? So are there any questions about the concept of interrupt-driven input-output? as opposed to polling type of input output. No questions?
Yeah, how does it work at a hardware level?
How does it work at a hardware level? Okay, that's a good question. So I can explain that just a little bit. Okay. So let me pick a pen. Hopefully, that has enough, ink in it. Okay. When you look when you look at this at a hardware level, so let's say this is my CPU or the processor, and for this particular example, this is my keyboard controller. The keyboard controller is typically a chip. Now it is integrated into a much more massive chip, but in the good old days it is its own chip. So the keyboard controller, with one end, it would have wires connecting to the actual keyboard. Okay. So when you press the key on the keyboard, it is actually closing the circuit, and by its own mechanism of scanning the keys, the keyboard controller can notice there's a state change of a particular key. Okay. And that will basically cause the keyboard controller itself, which by itself is some kind of a processor, is a very small, minimalist kind of processor, but nonetheless, it can do some processing. So the keyboard controller will do some processing and notice and say, oh, okay, this key here has just been released, or it just has been pressed. So in other words, as far as the keyboard controller is concerned, it can only register key press and key release. It doesn't know what key it is. It's only a key code that it can recognize. Okay, so the keyboard controller recognizes a change. So it will buffer up that change here. So internal to the keyboard controller, it's going to remember and say that, okay, now we have a key event that just happened. I don't know what to do with it. I just know the key code, and I'm not going to process it. So what will happen here is the keyboard controller has a line going to the processor. This is usually called an interrupt line. Let's see, there's a name for that. IRQ, interrupt request. Okay, and typically it is a negated line, which means when it's inactive, it has a high voltage. When it is low, it is actually active. It is also called active low from the hardware perspective. But that polarity is not important to us, when we look at it from the software perspective. So at some point, this signal is going to be activated or asserted. When it's asserted, the processor has its own interrupt controller inside the CPU itself. This is called the interrupt controller, which is a component of a processor. Okay? The processor can only execute, back then at least, can only execute one instruction at a time. So when you're executing one single instruction, in other words, when your microcode is still executing for a particular instruction, it doesn't care a single thing about the interrupt request lines. It doesn't do anything. Between instruction execution, the interrupt controller will basically say, okay, let me see if someone needs your attention. Okay? So when the interrupt controller looks at this IRQ interrupt request line and say that, hey, somebody needs your attention, then the processor will then say, okay, how am I going to process this? So that's basically what happens at a hardware level, is that is physically a line going from the keyboard controller to your CPU that is kind of like, it's kind of like when you go on a Muni or most buses, you have a button to press to request the bus to stop at the next station. That's the line. Yep.
Does the keyboard controller have a stack of its own? Does it have a stack of its own?
It does not have a stack. The keyboard controller has a limited buffer, but it's not organized as a stack. It's organized as a FIFO, first in, first out. So it is possible, if the processor is not paying attention or it is ignoring the interrupt requests, it is possible that you can press enough keys on the keyboard that you will start to lose additional keyboard events. And that's when you hear that beep, on the keyboard is, if your operating system is ignoring the request, is not clearing these events, then at some point the keyboard controller cannot store any additional events, and then you will start to lose those additional events. That's a good question to ask. Okay, so that's basically live without interrupts is polling, and I just explained all of these points here. So let's move on to interrupts. On the processor side, we have okay. there's the interrupt request line. The question now from the software perspective is, what if the processor says, okay, let's deal with this. Okay, what is going to happen? Well, it will take a look at which interrupt request line is asserted, because most processors have multiple IRQ lines or multiple interrupt request lines. You have one coming from your UART. UART stands for Universal Asynchronous Receiver Transmitter, which is typically what we used to connect to modems in the good old days. You guys probably have not seen a modem before, except in the picture, right? But we have multiple, IRQ lines. So this may be IRQ1, and we have IRQ2, and so on. So all of the interrupt lines that go into the processor, and the processor can associate a particular address in memory space depending on which interrupt line we are talking about. Okay, and those are called jump vectors. Okay, a jump vector, a unique jump vector, is associated with each hardware interrupt line. So when one interrupt line is asserted, the processor knows, okay, I need to go here to get to the instructions to process and to get to handle this particular interrupt. Are we doing okay so far with that concept? Okay. So that's the first stage of processing. When the processor is done processing, let's say in this case, a key event, what is it going to do? Now remember, the processor is usually doing something, unlike me. Okay, so the processor is doing something. Okay, especially in the game, it is going to calculate the coordinate of something, rendering something on screen, or something else that requires the attention of the processor. So the interrupt, or this line asserted, is actually interrupting the processor when it's actually doing something useful. Okay. When the processor is interrupted, the first thing it does is to remember its current point. It is equivalent to me grading your exam in my office, and then Chris comes in and with a question. So the first thing I'm going to do is to write down on a little piece of paper and say, okay, I'm grading question number 4 of this particular question, of this particular student. And then I'll go, answer, the question. When I'm done with, answering the question, I will look at that little slip of paper and go back to where I left off in terms of grading. In the case of the processor, it is pushing the return address on the stack to remember what it was doing before, and then it will transfer control to the ISR, or the interrupt surface routine, which is kind of like a subroutine, except it is not called from software. It is quote-unquote called from hardware. When the ISR is done, when the interrupt service routine is done, it will do a regular return to go back to where the processor was doing before and continue that operation. Am I doing okay so far with that analogy? So if you look at a timeline kind of like this, so we have ISR code here, and then we have, for the lack of a better word at this point, we'll call this background code. So the processor may be doing a lot of background code all along, and then the interrupt happens. So it will transfer control to the ISR after saving its current address with the background task, perform whatever the ISR needs to do, and when the ISR is all done, the interrupt surface routine is done, it will return back to where it left off in the background task and continue execution in the background. Are we doing okay so far with this concept? Yep.
You can tell me this is just way off base and take us on a tangent. Is that kind of how threading works or not?
Is it how?
Threading works or not?
How?
Threading. Threading.
Multi-threading.
Like you
Threading?
report a process.
It is related to threading, because what threading does, or what triggers threading, is this is a timer interrupt, and the timer interrupt will actually take control away from quote-unquote background 1, and then it will resume control in background 2 sitting somewhere else, and then when background 2 is getting interrupted, you can resume control to background 3. So that's how transfer that's how we can transfer control between the different quote-unquote backgrounds, and each background being a thread And you can have multiple threads in the process, and then you have multiple processes in the system. So it is closely related, but it's not like you can return like this. So when you have multi-threading, you just go over to the other one by saving the state of this background first. So you're not saving only the return address, you're saving everything, including all the registers and everything related to a particular thread. That's a good question. It is related to multi-threading, but multi-threading has a lot more to say as far as the state is concerned than just the return address. Right. So this slide basically talks about how we transfer control from quote unquote the background to the ISR, and when the ISR is done, we have a special return statement or return instruction to pop the return address from the stack so that we can resume execution to whatever code was interrupted to begin with. Okay, so far there's nothing here that has to do with our main topic. How do we interface with the operating system? This has nothing to do with it. Okay, on the device side, I'm not going to talk too much about this part here because it's not really related to what we want to talk about. Okay, so we are going to skip this one too because we already know the advantages of interrupts is you don't have to burn processing time unless it is needed. Okay, so this is the important part. The background process is probably running some kind of program that belongs to a user, that the user starts. Okay, so it can be a game, can be work processing, can be a lot of things that an end user would do on the computer. Would you give an end user program the permission to access the I/O registers so they can directly access the SATA controller and say, I'm going to spill out this content onto those sectors on the hard drive? Would you trust an end user application to do that? Probably not. So that means the background process or whatever the interrupt is, whatever the hardware is interrupting, should probably run at a low privilege level. So in case of any type of bug, any type of bad programming, it will limit its damage to just the application itself. What about the ISR? What happens when you limit the ISR the same way you're limiting an end user program? You can only do this, do these simple things. Do you think an ISR can do what it is supposed to do? What do you think an ISR needs to do? Let's think about what kind of stuff can generate interrupts. What do you think? A keyboard controller for one, okay, but an error. An error. An error? Okay. Well, errors of hardware tend to generate interrupts too. So in that case, the ISR basically has to decide what to do, how to fix that error. What about your SATA controllers? Do you think your SATA controller would generate interrupts? Yeah. And if so, why would it generate interrupts? Okay. What do you think your SATA controller would do? What is the job of your SATA controller? What is SATA? Serial ATA. And what does it do? What does it interface? It interfaces with mass store devices. So you can hook it up to a hard drive, you can hook it up to an optical drive like a CD-ROM drive or DVD writer and stuff like that. Why do you think it requires the interrupt mechanism? What do you ask a SATA controller to do?
Read and write data.
Read and write data. Okay, very good. Okay, so typically you would ask a SATA controller and say, hey, talk to the hard drive attached to you and go to this sector over there and write 4,000 bytes from this location. Okay, would that be kind of like a typical thing that you think your SATA controller would have to do? Okay, fairly typical. How long would that take, writing those 4,000 bytes to a few sectors on your hard drive? To you, not much time. To the processor, a lot of time, right? Because what if the disk head is not on the track that it is supposed to go to write that content? Then you have to move the disk head first, okay? How long does it take on the average for a modern hard drive to seek from one position to another track? Just approximate order of magnitude will be fine. A few milliseconds, okay? I would say 8 milliseconds is kind of like a average these days. Okay, 8 milliseconds is not a whole lot of time. 1 millisecond is 1,000th of a second. So 8 milliseconds is about 1/100th of a second. To you and I, it's an instant of time. Okay, we hardly notice 8 milliseconds has passed. What is the clock rate of the processor again? 3 point something gigahertz, right? 3.1 gigahertz. Let's just call it 3.0 gigahertz. Okay. So with 3.0 gigahertz, and we know that with modern architectures, because it has multiple cores, and within each core it has multiple ALUs, we know that we can execute at least one instruction per clock cycle. Okay, that's a very generous and very conservative estimate of how much processing can happen. So how many instructions can we execute in 8 milliseconds?
Did you say it was like a billion or something like that? It was around a billion?
Well, not quite a few billion. Okay, so this tells me that we can execute 3 billion instructions per second, right? This is one. Okay, let's just call it 1/100th of a second. So we are basically saying we can execute this many instructions, 30 million instructions. Just for the time that you have to move your disk head from one track to another track. Okay. Now, without the mechanism of interrupts, what do you think the operating system has to do? It has to wait, right? You tell your hard drive controller and say, seek through that track and then write 4,000 bytes to that section. Okay? And in between, you'll be waiting for the duration of 30 million instructions that you could have used to do something useful. Is that making any sense? So why do you think interrupts is important in this case? Because what you can do is you can send a command to the SATA controller and just give it all the parameters. Okay, this is the source where you're going to copy a chunk of memory or content. This is the track that I want you to write to, and tell me when you're done. And then you just walk away to do whatever you need to do. So the hard drive controller, the SATA controller, is going to do all this stuff here, moving the track over, and when it's all done, the SATA controller will cause an interrupt and tell the operating system and say, okay, I just did what you asked me to do. If at that time there's more stuff to write in the hard drive, then the operating system can kick in and say, oh, you know what, I got more stuff for you to do now. So the operating system is not going to waste the time of 30 billion instructions just for the hard drive to move from one track to the next. Is that making any sense? Is that okay? All right. Now, getting back to the main question. The main question is, what do you think the ISR, the interrupt surface routine of your SATA controller needs access to? Do you think it would need access to the registers of the SATA controller itself? No, it does. Okay? So that means when you're executing an ISR, you will need elevated privilege levels. Okay? You will need access to the I/O registers and a lot of other resources that your user process cannot have access to. Is that making any sense? Because an ISR interrupt surface routine has to directly interact with low-level hardware devices. An end-user process does not. Is this reminding you of something that we were talking about at the very beginning of this discussion? Privilege elevation. The interrupt mechanism, in order to transfer control from the background process to an ISR, this transition is not only continuing execution somewhere else, it's not just saving the where to go back to the background task, but it's also causing, in hardware, it's causing the processor to execute instructions in a higher privilege level, just so that the ISR has full access to all the hardware registers and also physical memory itself. That okay? Now, this is now executing at a high privilege level. We'll use a crown to denote that mode. Okay. When the ISR is all done, it has to return control back to the user process, right? So when you return from here to here, what happens to the privilege level? What should happen to the privilege level? Drops. It should drop back to whatever the user process is supposed to have, right? It should be lower. Is that making any sense? Well, isn't that what we want to do when we ask the operating system to do something? So the requesting process, the user process, it has to run at a lower privilege level because we don't want end user process to have access to important system resources to mess around with everything else. Okay? But when it's requesting a service from the operating system itself must have higher privilege level just so that it can do what it is supposed to do. When the operating system is done doing what you requested to do, it has to return control back to you as a user process. But that transition also has to change the privilege level back to a user level. So that means everything that we need to do to surface interrupts is also what we need in order to request service from the operating system. Is that are you guys making a connection between interrupts and user process? Yeah. I was awarded the Free Software Foundation Award for Advancement of Free Software this weekend, bracket 1. I've been given some forewarning that time thinking about how free software had influenced my life, it turned out that it was a lot. It's a lot. I wonder who wrote this. Screensavers.
It's an RSS feed from the author of X Screensaver.
Okay, so that's we're going to leave today's lecture at this point. We're basically just making a parallel between hardware interruption and ISR system. There's no homework assignments right now, so you guys have one weekend that you can enjoy or do the homework of other classes.